Let's compare Green's theorem versus Stokes' theorem. Now, really, Stokes' theorem is just a generalization of Green's theorem. So what's going on is you normally have the integral of this vector field, capital F, dot dr, over a curve C, and the point is that this turns into either the double integral over a two-dimensional filled-in region D of the curl of F dotted with the vector K dA. Okay, this is what happens if F is a two-dimensional vector field. So you just temporarily extend this to be a three-dimensional vector field, just insert a comma 0 there when you're computing the curl. Or if you have a three-dimensional vector field, capital F, outright, then you're doing the integral over the surface of the curl of your vector field F dot n ds. Okay, if F is P, Q, R. And so why is this a generalization? Well, really the only key thing to look at is that this K now becomes an N, and the thing is, this K vector that's the Z component, right? So that's the vector that's always pointing upwards, up in the sense of the Z direction, and that changes to becoming an N vector, meaning just the normal to the surface can be any which direction once you're talking about a surface in three-dimensional space. When you're just talking about this two-dimensional surface that lives in the two-dimensional plane, but you pretend that it lives in the three-dimensional plane, then the normal vector just has to point upward. There's a couple other loose ends I'd like to try to start tying up. And so first of all, we just saw one of these here was that Green's theorem. You can really think of it as if Green's is just a special case, if viewed correctly, of Stokes' theorem. Okay. Another thing to try to talk about some loose ends is curl and circulation. A lot of what we've done is mostly just try to read through theorems, what is the theorem saying, and then just try to apply the theorems without thinking a lot about some of the details. Even though people want to ask about these details, it's hard to, there's sort of like a need to just do some computations first, right? So, but let's now start talking about some of these. So first of all, let's just take this integral here, the integral over the surface, curl of F dot n ds, and that becomes this. I'm just going to rewrite the C to be boundary of S. So in line integral over the boundary of S of F dot dr. Okay, so this part right here, curl of F dotted with N, well, what's that trying to get at? Well, you have some surface here, right? So, there's some towel that got frozen in space. Okay, so there's your surface. And at each spot, there's a curl.n. So that's saying, how much along the surface itself, and there's like here, there's a bit of a hill, upward hill as you travel. And so if you draw this curly arrow thingy, but at each spot it has to lie within the surface in an instantaneous sense, how much curl is, how much is the water turning motion-wise at that spot in the towel? And the thing is, the interaction of this and that will cancel each other out, so to speak, right where these two meet, because one of these arrows is pointing in the opposite direction of the other in that spot. So what that amounts to, after all those cancellations are done, you're really just left with what's the effect of the vector field just along this outside edge right here. So that, let's just put this F back here. That outside edge, of course, is the boundary of S. And so talking about what happens as you travel along the outside here in this counterclockwise fashion, what's going on with the water there? Talking about how much water moves along this path in this manner is called the circulation. So this integral here goes by the name of circulation. Okay, so if curl right there, and computing the correct amount of curl relative to the surface is a microscopic circulation or movement, circular movement, then circulation is a macroscopic circulation or circular movement. We have a similar loose end to try to tie up with divergence and flux. So same deal, like curl, divergence, those were just computations done at each individual spot in a vector field, right? And there's this divergence theorem that triple integral over a three-dimensional solid region E of the divergence of a vector field, dv, is equal to the double integral over the closed surface, which happens to be the boundary of E, of f dot n ds. All right, so what's this divergence of f business? It's trying to quantify at each spot, at each point x comma y comma z, how much does the air or the wind or the water or whatever move away from that specific point. So you have this three-dimensional object. So I'm going to try to draw some. It doesn't have to be a flat cube, just whatever three-dimensional object this is, and it's filled in on the inside. I just don't want to fill in all the shading. That'll just get messy. But at every specific point, like right here, there's a discussion of how much is the point like right there, here, acting like, the explosion of the Big Bang Theory, right? And if the number is positive, you have a positive divergence at that spot. But then the next spot over, just right next to it, here, you'll have the work of the divergence between two points that are right next to each other, because one arrow points to the right and then one arrow points to the left. Those will cancel each other out. So what are you left with is what happens on the outside here. How much water is leaving through the boundary of these surfaces in all these directions. That's what's left after. That's the non-cancelled out part, and that's what this integral here represents. This is the flux.